Hey, welcome back to the lecture. So now let's implement this task delete exercise. Now here in this application, I'm not using actually the Sega files, so you can use if you want. All right. So now let me explain this code. Very simple. Here we are creating two tasks. The priority of task 1 is 1 and the priority of task 2 is 2. And after that, we are starting the scheduler. That's fine. And in the task 1 handler, it is very simple. Here you can see that the task 1 handler should toggle the LED for every 200 milliseconds, right? So let's do that. So let's go to the code and let's me call the RTOS delay function, which we implemented in the previous exercise. So the task 1 handler is very simple. Now let's take a look into the task 2 handler. So here you can see that it reads from the button here, and if the button is not pressed on the Nucleo board, then it toggles the LED for every 1 second. So let's do that. That is 1000 milliseconds. But if the button is pressed, then we will come here and the task 2, it should delete itself. And for that, let's use the API vTaskDelete. So the vTaskDelete is the API in order to delete. So here you have to mention the task handle, right? But the task 2 is deleting itself, isn't it? So that's why need not to use the task handle here. So if you want to delete some other task, then you have to mention the handle of that task. That's it. Very simple application. And here I would suggest you to raise the stack size, because you are making too many calls here, like you are calling the vTaskDelete, which is another pre-RTOS API. So stack may be consumed more than this. I'm not very sure about that, but for the better side, we can make it as around 500 words. So let's increase this to 500 words. All right, so that's it. And now let's build this project and let's see how it goes. So now let me just program this chip. So this is task delete demo. So let me just clear the buffer and let me just reset the board, and here you can see that the task 2 is running. So task 2 will always run, and you can see that the LED is toggling with a duration of 1 second, right? Let's press the button. So you have to long press the button for at least 1 second. So let's do that. And here you can see that the task 2 is getting deleted and task 1 is running. So let's try that once again. Let me reset. And remember that while pressing the user button, long press for at least 1 second. Here it is. All right, and you can see that the LED blinking frequency is increased. That means it is toggling with 200 milliseconds of duration. And one more thing I have to mention here is that once the task is getting deleted, so what's happening? So remember that once the task gets deleted, the task 1 is running, isn't it? So there is no space in this application to schedule the idle task, right? So that is actually bad. Why? Because when the task 2 gets deleted, remember that the memory allocated to the TCP and to the stack will not be freed. Remember that. So it will be freed by the idle task. So that means you should give provision in your application to run the idle task. So it may be okay for this application because here there is only one task, but when you design complex application where many tasks are created, and if any task is getting deleted, then you should allow the idle task to run, otherwise the memory will not be freed, and that may cause memory related issues in your application. So in this application, what I would do is here, in order to allow the idle task to run, so instead of using this RTOS delay, so in the RTOS delay, actually what happens, the LED task actually hangs here, right, in the while loop. So that means it will be keep executing on the CPU until the delay is met, right? So instead of doing this, we can call, there is one more API which I'm going to cover a little later, that's called vTaskDelay. So let's mention 200 here. So this also does the same thing of producing 200 milliseconds of delay. But the thing is, if you call this API, then what happens is the LED task will be blocked. That means it will be removed from the ready queue for 200 milliseconds. So that means it will not be scheduled to run on the CPU for 200 milliseconds. So that allows the time for idle task to run, so that idle task can run and it can do its freeing task. So this application also works same. So no change with the output, but the only thing is, so in this case the task 1 was busy and it was fully engaged to execute on the CPU. But if you use vtask delay, then the task 1 will be blocked. That means it will be put into the blocked state for 200 milliseconds, and after 200 milliseconds the RTOS will unblock that task to run on the CPU. So in the meanwhile, the idle task can run and it can do its job. So I would suggest you to take the trace and analyze the trace. So I'm not going to take the trace of this application, but you can always do that. Great. So I will see you in the next lecture.